Hello and welcome once again to a slide video show from the Cornish Radio Amateur Club, and we're going to look at transistor characteristics for the RSGB advanced examination. So in an introduction to semiconductors and in talking about the bipolar transistor, we looked at the structure of the bipolar transistor and we put it into a test circuit. And the test circuit gave us a voltage across the emitter and collector, shown by the battery there on the bottom, and a voltage between the base and the emitter, shown by the smaller battery just above it, and a switch to switch the voltage on the base on or off. With the switch open, no current flows into the base region and no current flows in the collector emitter circuit. And this is due to the depletion region, principally between the base and the emitter. If we close the switch, then current will then flow into the base, and this will have the effect of bringing the charge carriers together and allowing current to flow, a larger current to flow in the collector emitter circuit. So this small current, perhaps a few microamps, into the base causes a larger current to flow in the collector emitter circuit. And the current flowing in the collector emitter circuit could be perhaps of the order of milliamps. So if we superimpose a small signal, a small AC signal, onto the current flowing into the base, that will produce a larger AC fluctuation of the current flowing through the emitter collector circuit. Let's have a little look at these. The DC current, as we've said already, the small DC current flowing into the base produces a larger DC current flowing in the collector circuit. And for the RSGB exam, we need to know that that current gain, beta, is equal to the collector current divided by the base current, the large over the small being the gain. And by now we should be able to change the subject of the formula, where we have three variables. For example, we've been doing it with V, I, and R. We can state V equals IR, I equals V over R, or R equals V over I. Similarly, if beta equals IC over IB, then beta times IB equals IC. Now you can do that by changing the subject of the formula algebraically, which is probably the preferred method, or you could construct one of those triangles to do it that way. If we're going to do it algebraically, we could look at the top formula, current gain beta equals IC over IB, and we multiply both sides of that equation by IB. So then we end up on the left with beta times IB, and on the right we get IC times IB over IB, and the IB on the top and the bottom of that fraction cancel out to give the lower equation. Now we've said that if we superimpose a small signal onto the base current, we get a larger signal in the collector circuit. And the signal gain would be that large signal divided by that smaller signal. And for bipolar transistors in common emitter configuration, and we haven't covered that at the moment, but if we can just remember that, for bipolar transistors in the common emitter configuration, we call that HFE. And you will see that in literature about your chosen transistor. And HFE equals small I C over small IB. In other words, the signal on the base, the signal on the collector divided by the signal on the base. And I've labelled it as small I rather than large I to distinguish between the DC component and the signal component. Now for this exam, for all practical purposes, the gain, beta, is approximately equal to HFE. And we don't go into detail about the H parameters of bipolar transistors. They're not used, there's only two really used, HFE, H forward emitter, and HRE, reverse emitter. But for us really, HFE is the only one worth mentioning, and it's good enough to know that that's going to be, for all practical purposes, about the same as beta. Now we're going to see values for beta of perhaps 20 or 25 for a large power transistor. Large power transistor, its purpose is not particularly to give a lot of gain. Or you might see values of 3, 4, 500 for a small signal transistor whose purpose is to provide gain. Now we've said that the transistor is not switched on unless it is forward biased. And here's a circuit to forward bias a transistor. This is a circuit that you used in the intermediate course for the demonstration of transistor as a switch. Transistor connected, in this case between a positive and a zero rail, and a resistor in the collector circuit to limit the overall current going through the transistor so it's not damaged, and similarly a resistor connecting the base to the positive rail in order to forward bias the transistor. And provided the forward rail is over a couple of volts, in other words enough to provide a voltage on the base more than 0.7 to forward bias the base emitter junction, then that transistor will conduct because it is forward biased. And you should be able to recognize that circuit for the exam. Now let's look at some voltages on a transistor and how they're called. Common sense really. Here there is the diagram on the left showing the physical structure of the transmitter, and it shows currents going through the emitter, base and collector, labelled IE, IB and IC respectively, and voltages between the base and the emitter, VBE, and voltages between the collector and the base, VCB. So there they are shown on the structure of the transistor on the left and on the circuit symbol on the right. And here we have an additional equation, IE equals IB plus IC, or the current flowing through the emitter is equal to the base current plus the collector current. Now, that is just really an expression of Kirchhoff's law, which we've covered in an earlier video. We don't need to remember that, or indeed know it or use it at all for the RSGB advanced exam. We just need to remember the current gain, beta equals IC over IB. But using those two equations together, you can see that you could start to derive more information about the bipolar transistor. Now let's take a moment to look at a practical example of a transistor switching a relay. If we had a small voltage that wasn't able to provide enough current to switch a relay, then we might use a transistor to provide that current. And the circuit is shown there on the screen on the left. So the top rail labelled plus VCC, and the bottom rail 0 volt. And there we have an NPN transistor, which is a BC109, a very common and cheap transistor. The relay is in the collector circuit, and the flywheel diode there is just there to protect the transistor against inductive spikes which occur when switching on and off inductive loads. And we'll have a look at that later on. But for now, it's enough to know that if collector current flows, the relay will close and the contacts NC, NO will be switched. NC standing for normally closed, and NO standing for normally open, and C standing for common. So we had a small signal coming in at V in on the left. That would cause a current, we hope, to flow into the base, which would cause a larger current to flow between the in the collector emitter circuit, so that the current flowing through the collector would switch on the relay. Now when we have no signal, we don't want any current to flow. So the 10 kilo ohm resistor on the base ensures that when V in is 0, the base is at the same potential as the emitter and no current flows through the transistor. When a small signal is applied, let's say 2 volts, that 2 volts is developed across the potential divider made up of the 1 kilo ohm resistor and 10 kilo ohm resistor. And I've depicted this in an equivalent diagram on the right of the screen. So the voltage then on the base will be slightly less than the 2 volt applied because it's a potential divider. But it will forward bias the base emitter junction and current will flow. So if we had a pulsed waveform shown there with a 0 and a 1, maybe it's 0 and 1 volts, that would be sufficient perhaps, or 0 and 2 volts. And if that was coming in at V in as a signal, then a reasonable impedance would be presented, or resistance would be presented to that signal of the order of 11 kilo ohms, slightly shunted by the base emitter, because remember 60 microamps or so might flow into the base, but a reasonable impedance so as not to affect the signal source, and the relay would pulse in time with the signal coming in on the input. So there is a practical circuit and a circuit we now are able to interpret and do some maths around to understand what's going on. We could look at the current gain, and we can look at the resistance or impedance presented to the signal. So it's also important to remember that the base current determines the collector current, not the voltage between the collector and emitter, not VCE. So if we go back to the previous slide, we have VCE, and sometimes we've written it there as VCC, but it's the same thing for practical purposes. So here we have a circuit with perhaps 10 volts on at VCE between the collector and the emitter, and we have no current flowing in to the base because the variable resistor shown on the left hand side of the diagram in the base circuit is set to a very high value, and so virtually no current flows into the base, and so no current flows through the collector emitter circuit. And if we change the VCC, or VCE rather, if we change VCE, you can see on the graph there we're changing it between 0 and about 24 volts. Still no current flows in that circuit because no base current is flowing. If we now adjust the variable resistance in the base circuit such as 20 microamps flows in the into the base, and we similarly alter VCE between 0 and let's say 18 or 24 volts, this is the graph we get. It's labeled 20 microamps because that's the base current that's flowing, but you can see that virtually for all values of VCE after some sort of value, the current flowing in the collector circuit is half a milliamp. And we need some sort of voltage across the collector emitter circuit because otherwise the charge carriers going into the base don't get hoovered up by the collector, and therefore no collector current will flow. But that happens very, very early on with very small voltages. Similarly, if we increase the base current to 40 microamps, virtually independent of what we put on the top rail as VCE, we get about a milliamp flowing. And it's the same picture if we increase the base current to 60 microamps, virtually independent of VCE, we get about 1.5 milliamps flowing. So what we're saying here then is that, and we're restating it, that the current through the transistor, through the collector emitter circuit, or if you like the collector current, is determined by the base current, not by VCE. Let's have a look here then at a biasing circuit. If we had a resistor between the positive rail and 0, and it was a variable resistor, and I've marked, if you like, voltage points between 0 and 10, we can see then that if we have a base emitter voltage of 0, we don't get any current flowing. If we have a base emitter of about 0.5 volt, we're starting to see a little bit of current flow. We see the knee when we increase the base emitter voltage to 0.7 of a volt, and then at 1 volt and onwards we see collector current flowing. So this is showing the biasing effect of a on the base and the effect it has on collector current. So thank you very much indeed.